Hello, good day everyone. So today our discussion is about finding domain and range of a function. So let us first start with linear function. Okay. The domain and range of a linear function are all real numbers. There is no restriction. An example of this, so we have f of x equals 3x minus 2, and as you can see that is linear because the degree of the leading term, which is 3x, is 1, and from that we can say that the dominant range are all real numbers. Next, so we have quadratic function, and the domain of a quadratic function is all real numbers. And for you to find the range, you just need to find the coordinate of the vertex or the parabola. Okay, the vertex of a parabola. In order for you to find the x coordinate, you may use this formula, negative b over 2a. Okay. So a is the coefficient of the leading term, as you can see here. B is the coefficient of the middle term, and those values will be used in order to find the x coordinate. And once you already find the x coordinate of the vertex, you will substitute the x coordinate in your given equation so that you can arrive or get the y coordinate. And after having this y coordinate, you just need to analyze it. Okay, so we have this given condition. If your a is greater than 0, then your y coordinate is the minimum vertex, no? It's the minimum at vertex, and you just need to follow this format. This will be your range. Okay, your bracket, y coordinate, comma, positive infinity, parenthesis. Okay, if your a is less than 0, so your y coordinate is the maximum at vertex, and this will be the format of your range. So you have parenthesis, negative infinity, comma, and then your y coordinate bracket. So okay, so let's have an example. So we have f of x equals x squared. Okay, so as you can see here, okay, by following the format, a x squared plus b x plus c. Okay, so our x squared here is the leading coefficient because it has a degree or exponent which is 2, and its corresponding coefficient is 1. So this will be your a value. So how about the b? So as you can see, there's no middle term, but we can write it as 0 x, meaning that our b value is 0. So if you're going to simplify 0 times x, that is basically 0. Okay, to calculate the x coordinate or to solve for x coordinate, so that we will use the formula negative b over 2a, and since our b is 0 and our a is 1, so we have 2 times 1 here, so this gives us 0 as our x coordinate. And in order for you to find the y coordinate, you just need to substitute or evaluate the function at f of 0. Okay, so this will be 0 squared, and then we have 0 as our y coordinate. And then let's analyze, okay, the vertex, if it is if the y coordinate is at minimum or maximum. So again, going back here in the condition, since a is 1, therefore it satisfies this first condition, right? 1 is greater than 0, so therefore the minimum, or the y coordinate is the minimum at of the vertex, right? And we will use this format to write the range. So that will be, so our range here, it will be parenthesis, it's bracket 0, the y coordinate, comma, infinity, then parenthesis. Okay. Next, cubic functions. So cubic functions, the domain and range of this function are all real numbers. So example of this cubic function, so we have this f of x equals x cubed minus 2x squared minus 3x plus 3, and then as you can see here, the leading term is x cubed, and the exponent or the degree is 3, so that's why it is a cubic function. Okay. Next, so we have rational function. When we say rational, it is a fraction, okay? A fraction where the numerator and the denominator are polynomials, usually polynomials. Okay. To find the domain and range of this function, usually we have this constraint in rational functions. So our constraint here is that the denominator should not be equal to 0. Okay. So given this example, we have f of x equals 1 over x minus 2. So just focus here in the denominator. Okay. Just focus in the denominator and then equate, no, from that expression, okay, equate it, or that x minus 2 should not be equal to 0. Okay. And then solve the inequality. So basically you need to transpose this negative 2 to the other side. So we have x is not equal to positive 2. So this will be your domain. Okay, this will be your domain. But if you're going to write it in a interval notation, okay, so this will be the answer: negative infinity up to 2 union 2 up to positive infinity. Next, as for the range, okay, we have this general step, but usually, okay, we equate or solve for x in terms of y when looking for range here. So to do that, we just need to set f of x into y, okay, and then we have 1 over x minus 2 here, and then solve for x in terms of y. So we just need to change, no, instead of our equation is equated in y, so we just need to equate it in x. So we have y, or xy here, minus 2y equals 1, and then transpose 2y, so we have x y equals 1 plus 2y, and then divide both sides by y so that we can get in x, no, in the left side only. So this will become x equals 1 plus 2y over y. So we already equate, okay, or we already solve for x in terms of y, right? So next, apply the constraint here. since it is a rational function also, so let's apply the constraint. Where our constraint here that is that y, or the denominator rather, should not be equal to 0. So just focus on the expression in the denominator. So we have y here, and that y should not be equal to 0. Okay, so that's it. So that's the domain. Okay, I mean the range rather. So that's the range. Okay. And if you're going to express it into interval notation, so that will be negative infinity, comma 0, okay, parenthesis, union, parenthesis 0, positive infinity, parenthesis. So this is the general way of finding the domain and range of a rational function. So we have this pre-assumption. So let's assume that the domain and range are all real numbers, and then apply the restriction. Okay, so to find the domain, first is do not simplify your given function. Okay, then check for the restriction. Again, the restriction of a rational function is that the denominator should not be equal to 0. Apply that. Okay, focus on the denominator, apply the constraint, then solve the inequality. Next, so sometimes we have this discontinuities. Okay, let's say we have x plus 3, we have f of x equals x plus 3 over x plus 3 here, and x minus 3. Or should I move this part here, this one? So let me have x plus 3 here and x minus 3 in the numerator, and then in the denominator we have x minus 3. So okay, so here in this given example, so our constraint here again is x should not be, or the denominator should not be equal to 0, and by focusing in the denominator we have x minus 3, and then apply the constraint, so that should not be equal to 0, and then solve for the inequality. So this will give us x should not be equal to positive 3. So this will be the domain. Okay, this will be the domain, and if you're going to graph it, there's an open hole here. Okay, let's say it is a graph of, let's say this is the graph of this function now. So it is an open hole now if we're going to graph it. However, this open hole, okay, is a removable discontinuity. Okay, or this open hole is a discontinuity, but it is removable because if we're going to simplify this f of x, okay, this original function f of x, we can cancel out this x minus 3, and this will give us x plus 3. No? And if we're going to analyze, no, our new function, which is x plus 3, okay, there is no restriction here because it is a linear function. So going back here in our graph, okay, this discontinuity, okay, will be, or possibly be removed if you simplify your function. Okay, so therefore it is called removable discontinuity. So basically here we have open hole, and if you're going to simplify your function, this open hole will become closed hole. Okay, it will be part of the interval. So that's why it is a removable discontinuity. But again, we need to know the real behavior of our function. So that's why we do not simplify our function. Okay, we do not uh, we do not cancel out some fact or some terms here. We can actually we can simplify it, okay, but not in a way that we can cancel some terms, like this, like in this case, no, we canceled x minus 3, those factors. Okay, next, as for the range, so this is the general rule here. We can simplify, okay, the given function, no, we can start simplifying the given function to find the range, no. So after simplifying, uh, use these following conditions, no, in order for you to find the asymptote. So finding the asymptote gives you or provides you information what will be the behavior of your function in terms of range. Okay, so if the degree of your p of x, no, the degree of the numerator is less than the degree of denominator. So what I'm referring here is the degree of the leading term. Okay, again, if the degree of the leading term of the numerator is less than the degree of the leading term of the denominator, so the asymptote, you have we have a horizontal asymptote here, which is equal to 0. Okay, it's always set equal to 0. We have y equals to 0. Next, if the degree, okay, in the numerator is equal to the degree of denominator, so basically we have a horizontal asymptote, no, which is y equals the leading coefficient of p over the leading coefficient of q. Okay. Next, so if the degree of p is greater than the degree of q, so there's no horizontal asymptote here. And last, if the degree of p is equal to the degree of q plus 1, okay, if the degree of p is equal to the degree of q but added by 1, okay, so there's a slant or oblique asymptote in the graph. So when we say oblique, so it is a slanted asymptote. Next, after you already define the asymptote, the present asymptote in your function, okay, you can continue knowing the behavior by solving for x. Okay, it should be solving for x in terms of y. Okay, solving for x in terms of y. In terms of y. Okay. Next, so we have even root function, and the domain and range of this, okay, is that we just need to focus on the expression inside the square root. Okay, and the constraint here is that the expression should be greater than or equal to 0. That's the case for finding domain of this even root function. So let's say this one. So we have f of x equals the square root of the quantity x minus 1. Okay. So focus here in the expression inside the radical. So we have x minus 1. Apply the constraint, which is the expression should be greater than or equal to 0. Solve for the inequality. So we have x is greater than equal to positive 1. So this is our domain. And if we're going to write it into interval notation, so we have bracket 1, comma, infinity, parenthesis. Next, output. Always assume that the output of a f of x is always greater than or equal to 0. Because in function, okay, in function we're just taking the principal root or the positive value of a even root function. Okay, if you're dealing with even root function, we always get the positive value here. Okay, we all know that if you evaluate this expressions x squared, okay, you take the root, the square root of this x squared, so this will give us a positive and negative answer, two solutions, right? That is true when you're dealing with equation, but however we're dealing with a function. So in function, no, if you're going to evaluate the range of a even root function, it is expected that it is always a positive value. Yes, it could be 0, but again, it always positive, the principal root. And so going back in this example, we have f of x equals the square root of x minus 1. Again, the output are always greater than or equal to 0. So from this, we can express our interval notation as bracket 0, comma, infinity, parenthesis. This one. Next, we have add root function. Okay. In this case, the domain and end range are all real numbers. Example of this, we have f of x equals the cube root of x minus 1. Okay. So how do you find if your root is a even or odd? So by focusing on the index of your root or of your radical function. If the index is even, so therefore it is an even function, even root function. If your index is odd, so that is odd root function. Okay. In this case, we have f of x equals the cube root of the quantity x minus 1. Okay. So since our index is 3 and that is odd, so that is odd root function. And an odd root function, the domain and range are all real numbers. Next, the absolute value function. So if you encounter a function with this expression, two bars, okay, two straight bars, okay, with expression inside, so that's an absolute function, okay, absolute value function, and the domain of this function are all real numbers, and the range, it is always greater than or equal to 0. Okay, whatever is whatever the expression inside, it will give you always an output which is greater than 0. 0, it could be equal to 0 or greater than 0. Next, exponential function. So an exponential function, the domain of this is always real number. Okay, always real numbers. And as for the range, it always positive number. Okay, always, again, take note, it is always positive number and 0 is not included in the range. This is so we have this example, f of x equals 2 raised to x. Okay, 2 raised to x. As you can see here, this is an exponential function because we have base here, which is 2 raised to x. Okay, x is a variable raised to any variable. So that's, so therefore it is a or it is an exponential function. Again, the domain of this, it is, we have negative infinity to positive infinity, and for the range we have 0, again parenthesis 0 comma positive infinity parenthesis. Last, we have logarithmic function, and this is the inverse of exponential function. As for the domain, always positive, 0 is not included. Okay. The expression inside the log, okay, the expression inside the logarithmic must be positive, okay, positive value, and not equal to 0. Okay. Next, as for the range, all real numbers. So that's it. So that's how you find the domain and range of a function. Okay. Just remember that you can start uh, finding finding the domain and range of a function by classifying first the function. So what type of function it is? Is it linear, quadratic, cubic? Okay, so forth. Once you already classify it, okay, you may use this technique. Okay, so after finding the dominant range, you can now proceed in graphing a function. So this is the general way of how you graph a function. So first, again, you just need to identify the domain and range as well as the properties of this function. Once you already know the possible input values and output values, you can now choose values of x from the domain. Okay? And then those x values will be substituted in your given function so that you can get the corresponding y. Let's say you have x sub 1. Okay, that x sub 1 is substituted in your function, and that will give you y sub 1. X sub 2, y sub 2. X sub 3, y sub 3. So, once you already have those information, determine, okay, the next step is to determine the behavior of your x and y. Okay. Look at the values. Observe how your y changes as x increases or decreases. Okay. You can look for the patterns, like growth, decay, or is there symmetry or turning points in your given data. Then once you already analyze the behavior, so you can plot it in your Cartesian plane. Those x sub 1 and y sub 1, those x and y's, right? Plot it carefully on your graph. And then lastly, you just need to trace the curve, trace the plot that you have. Okay. Connect it, form a smooth line or curve, and then extend it based on the behavior of the function. So that's it. That's how you graph a function.